Hello and welcome to a tutorial on the very basics of natural language processing and more importantly its applications. NLP in fact is a branch of artificial intelligence that allows computers or generally machines to understand and interpret human language. The human language supplied can be both in terms of text, written text, or it may be in terms of voice commands. There are tons and tons of applications in natural language processing. Let me just go through a few of those and the related terminology. So, for example, to build a lot of other applications in natural language processing, one of the very basic backbone is modeling a language. For example, let's take an example of English language. So if we want to model English language, the goal here is to basically predict or find out the probability of a sentence. Let's say it's a sentence level. So given a sentence, what's the probability that this sentence, the words in a sequence, they occur in a particular way? For example, let's say the sentence has different words. For example, we play. Let's say we play football. Let's say. Then and then full stop. Now the goal of language model basically is to come up with the likelihood that given we and given play, what's the probability that it is the next word is football, or what's the probability that we play football? That we play football. The language model will give a likelihood for this, and similarly, we eat football, for example. So here this particular probability will be small. This particular probability will be large, but who is actually telling that? That's the language model. So modeling language, it relies on basically a very large corpus. Corpus is a technical word that is used in NLP community that basically refers to a very large body of text, English text available on Wikipedia and books and stuff like that. And the language model, the most modern language models, they are basically trained using recurrent neural networks that actually rectify a lot of sentences, sometimes autocorrect, sometimes give options, auto-completion and stuff like that. It also helps in speech recognition. For example, if a voice command or audio signal contains several words, and let's say there are two words that actually voice like same, they have same kind of voices, but they are two different words, then this language model actually will help to select one of the two words that may sound same based on the probability that which word will fit in the particular sentence. Language models, they also are useful in machine translation. For example, given English, let's say sentence, if somebody want to convert that English sentence into a French one, let's say, then language model actually is useful in generating this machine translation. For example, in generating from English to French or vice versa, what are the most likely words that should appear in the particular sentence? Although machine translation has its own a lot of training and stuff, which actually goes through a lot of supervised kind of training, but one aspect of that is also the language models that are there for a lot of corrections and removing a lot of ambiguities in there. And this is really desirable. For example, if somebody wants to convert from one language to another, maybe that's a written text or maybe spoken voice, that might be very handy. Think about having an app that actually is translating among several languages. It might need to mitigate for a user, for example, it may mitigate the need of learning all possible languages if you have a machine translator or a language translator. And using the tools of natural language processing, machine translation actually becomes very mature recently. Also, there are, a lot of experiments that went on sequence generation, for example. Now computers and machines, through natural language processing tools, they're able to now write, for example, text like Shakespeare, or generate music like other musicians and stuff like that. So for example, even now computers using NLP techniques, they can write very valid programs, computer programs in, for example, C++ language or Java language. There was an experiment where they trained actually an NLP model on all Linux source in C++. And then they actually generate a piece of code out of that trained model. And it turns out that the code was very valid with all kind of aspects of coding in context and in a lot of stuff. So, and for example, if you train your model on, let's say, the text of Shakespeare, then you can generate a similar kind of text, and it might be really hard to judge whether that's a text generated through a model or that's the actual text of Shakespeare. And that is also possible using natural language processing and the techniques and tools from natural language processing. Text summarization, sometimes we really want tools to, rather than go through all the text, we may want apps or software that actually come up with the summarization of the text. What is the most important point in the text? What's the summary of the text? What is the topic in the text? And this may actually save a lot of time going through all the text and figuring out whether that piece of text or a particular document is relevant to my query or relevant to my search or something like that. So using the techniques of natural language processing, the text summarization actually becomes really mature, and given a piece of text or a document, the summarization module can convert or compress the document in a very in a few words, so that you can get a look and feel of what the text is about. And if it looks like that, if the summary looks like more interesting, then you can go and read all the text. Otherwise, you can just skip that very quickly and go to the next document, for example, in case of searching something or searching relevance or something like that. Also, sometimes it is important to group a lot of different documents, written documents, in terms of their similarity. For example, all the documents related to supports, they should cluster or group in a particular folder or a directory. All the documents related to political discussions, they should group. Sometimes it is important to actually group a lot of data, and it helps us also to identify the documents for SEO, search engine optimization. When you want, for example, a particular kind of document, maybe you go for a particular group to search rather than searching it all over. And it has other benefits as well. Grouping means finding out the similar documents and suggestions and stuff like that. So natural language processing actually, the tools of natural language processing actually are dealing with document clustering today as well. Text classification, for example, people give different kind of reviews, maybe to, for example, restaurants, what kind of, so for example, the star reviews in restaurants, whether the food was excellent, good, bad, or what, or maybe the reviews on movies, or let's say you are given a piece of text and some predefined categories, and given the text, you want to find out the text fall in what kind of category. For example, the most important or most common text classification is a negative and positive review, for example. So given a review, written a review, you want to find out whether that review was positive or negative based on a particular product or maybe movie or something like that, so that the next time, whether based on positive review we actually give the recommendations, or based on negative review we may actually improve our business style and stuff like that. So based on text, these kind of classification models can also be built using natural language processing techniques. Also, speech recognition or sometimes speech to text conversion is really very important in building, for example, digital assistants and other stuff where you really want to control or command different devices using your speech. And also this speech recognition also uses this language model implicitly inside to actually come up with the better understanding of what is spoken. For example, I gave this example earlier as well. If two words they pronounce like same, maybe the language model will help you selecting one of those that is more probable. And there are tons and tons of other applications of natural language processing. So let me actually move on to actually a little bit detail of how things actually work inside. So all these applications, they are really high level applications and stuff like that. Seeing those is really a great motivation. But how things actually work under the hood. So given a piece of text, for example, there are different kind of features we have to compute, like we have to compute the features in case of images, in case of other kind of data. At the end of the day, these are machine learning models that are going to work, and they work on features. And the features are numeric features at the end of the day. There are several ways of computing these kind of features. Sometimes the features are computed on, for example, word level, given a sentence. For example, we play football. Let's say we play football. So sometimes the features are computed on word level, and we may actually convert a piece of text to different tokens. For example, if text consists of a lot of sentences, then tokenization might be to convert the sentences, a lot of sentences, to different sentences, and each sentence then will be a token. And then tokenizing a sentence means converting the sentence into different words. Then maybe features can be computed for each word separately using one-hot encoding. And one-hot encoding means, let's say you have a dictionary with words, let's say a, apple, and something like that. And let's say your dictionary contains a lot of words. Let's say ideally all the words in English in a particular sequence, dictionary sequence. And let's say this is index 1, this is index 2, and let's say there is a word here, let's say house, that has, let's say, index 32, 1, 3 to 1, and so on. So, and these are the indices. So we actually will be having, and let's say the total size of the dictionary, just for example, let's say is 10,000 here. Although it's much more than that, but let's say 10,000 most common words. Then the one-hot encoding of we is basically a vector of all zeros, but one at the index where we appear in the dictionary. So for example, if we appear in the dictionary at the index 100, then the index 100 here contains 1, and everywhere else it contains all the zeros. And this vector, feature vector, is basically a 10,000 dimensional vector where only one entry is 1, all the other entries are 0. Similarly, we can have one-hot encoding for play, the word play, and we can have one-hot encoding for the word football. And then these one-hot encoded vectors, they can be treated as feature vectors, and we can then learn different machine learning models based on this sequence of feature vectors. And the feature vectors really can be at document or sentence levels, like bag of words or TF-IDFs, for example. We can just count the different terms based on their importance, and sometimes the importance is calculated as which words are most common, like stop words, the, and, of. These are really frequent in a lot of text. So maybe we are giving less weights to those and most of the weights to the words that are less common or non-stop words by computing a document level feature vector, sometimes called the TF-IDF, term frequency inverted index. And sometimes these features are computed at document or sentence level, using bag of words or clustering like that. But most recent models actually deploy recurrent neural networks, and they actually rely on feature vectors that are word level rather than sentence or document level. One hot encoding is good, but it actually has problems that different one hot encoded vectors, although for two similar kind of words, their vectors are orthogonal. If you take the dot product of the two vectors, you get completely there is no similarity between two different one hot encoded vectors. Their dot product is always 0. Although the two words like king and queen, they might have certain similarities. So people came up with embeddings that actually use some of the random context and generate feature vectors that are more informative than one hot encoding vectors. And also the one hot encoded vectors, they have a lot of dimensions, and embedding vectors, they have less dimensions and they are more informative. There are several ways of computing these embeddings. The most common one is word-to-vec, negative sampling, or GLOVE. And there are models available that can actually compute word level embeddings. And these models, they actually are pre-trained on a large corpus of English text and maybe text of other languages as well. And computing the feature vectors using these kind of embeddings is much more informative and can improve the performance of the model significantly as compared to one hot encoding. Also, there are embeddings, very recent embeddings that actually use the context. The embeddings like word-to-vec, GLOVE, negative sampling, all these embeddings, they actually are context-free embeddings, meaning the same word, if appear that word in a different context, the embeddings will be same. However, the embedding with context, like the very recent embedding of algorithm BERT from Google, that actually take care of the context very, very sharply. I mean, the word appears in what context. Based on the context, the embedding is designed. So the same word in different contexts may have different kind of embeddings, which is really required to capture the context. Anyways, first of all, we have to compute the features for whatever tasks we are going to perform. And once we have the feature, or sometimes called the word level embeddings or encodings or feature vectors, then we are ready to actually train a model for whatever task we are really going to perform. And most common models in natural language processing for different kind of techniques, like building a language model, sampling a novel sequence, or machine translation, or maybe a text classification, the most common model is recurrent neural network. And the reason is the input length for different kind of sentences in terms of the number of words, they vary. And when you have, in case of, for example, machine translation, the input and output length, they both can vary depending upon the language linguistics. So when the input and outputs, they are varied in length in your training data, the most common choices in that kind of framework is neural network. It is true also for videos and for audio signals, we are varying different length, but text is something for which this recurrent neural network becomes most prominent. So the whole pipeline is, so for example, text classification, let's say, let me take an example of text classification. So let's say given a problem of text classification, you will be having a lot of text with, that's a training data. And each text sentence, for example, or a paragraph maybe, let's take that instance. It has either a positive review or a negative review. So let's say it's a binary classification problem. So what we will do is we will pick the text, we will compute its embedding, and depending upon the number of words in that text, there will be those many embedding vectors. So for example, if the first text instance has 7 words, then we will be having 7 embedding vectors. If the second piece of text has 3 words, then we will be having 3 embedding vectors for that. Now, because the length of input and output, they are varying, the best choice here is a recurrent neural network. So we will build a model, for example here, RNN model. And we will give the xt, which is the embedded vector, and we will compute yt. For in this particular case, we will compute the y at the in the unrolled very end. So yt, for example, y hat, and this y hat with the original y, we will compute a particular loss and apply a back propagation to actually learn the classification. This is true, for example, in the case of binary classification, or if we have multiple classes, we can deploy here a softmax unit, and So the real pipeline is given a piece of text as a training data, compute the embedding or the feature vectors, deploy a recurrent neural network. Mostly recurrent neural network works because of the nature of the varying length text. And once you have trained the model, then make inferences using those kind of model like ordinary techniques in machine learning. So that's a very brief introduction of natural language processing in the context of its applications and the use of recurrent neural networks and embeddings, feature vectors. The most recent kind of embeddings, they are learned by neural networks by themselves. I mean, they are no longer pre-designed handmade features. Actually, these embeddings, they are learned on large corpus of data and using these neural networks. So they're really powerful modern techniques, modern embeddings. They are really great, and the NLP really is improving a lot, particularly with the birth of BERT algorithm or BERT embedding from Google AI. Things they have changed drastically. So I hope you have liked our video. So please press the like button, subscribe our channel, and share this video with your fellows. Hope to see you next time.